Hi, you are again. They just connect the power here. Hi, Grinder. What's that? Let me turn off the video because I'm not going to use that much. I'm hardwired now, so hi, Joanna. I plugged in. I'm connected via the Ethernet now, so that should be a little more reliable. I should be able to hear you. Joanna, can you say something? Hi. That's no good. Oh, hi, Joanna. How are you? Okay. Okay. I just wanted to make sure that if I disappeared or if you had to tell me that my room was on fire, that you'd be able to tell me. God forbid. Okay, what do we got here? Probably want to show a, oh, I see, I'm going to go through, I need to turn on OneNote. And then I can go here. And I can share an applications, correct? Just an application and title page, share. Here we go. Hi, can anybody see that? Okay, I take it you can. Yep, okay, so let me go back again. You gotta go to the app. Oh, what am I doing? Oh, where was my hi? Okay, here's the hi. Okay. And I go to draw somewhere here. Draw, right. Take this eraser off. Okay, what have we got today? What we've got is we have some exercises, and we have some exercises, and we have some problems. So maybe what we'll do is go back here, and we will exercise 1, we have exercise 1, we have exercise 2, and we have problems 1 and 2. So there's 4 of them. Okay, so let's go for a polling, 4 choices, start. And what we have is 1 is exercise 1, 2 is exercise 2, 3 is problem 1, and 4 is problem 2. I always want to get this no response down to 0. There, we're down to 11. Keep on going. I guess one way to get down is, okay. Show responses. So we have here 18, 14, and one person has a question about exercise 2. So let's start with the last one first, and then we'll work our way back. Okay, so we're doing problem 2. And which says production rate of a steel fastener process is 120 parts per hour. So it produces 120 parts every hour. And the specification limits are 10 to 22 inches. That's quite a range, but okay. So it's got to produce the USL is equal to 22, and the LSL is equal to 10. So it's got to produce between 10 and 22. I like to think of these as microns maybe, but even that is a big percentage range. Anyway, the individual 20 individual fasteners are selected from the production process, and the in-control value of the process mean is mu equals 15 and sigma equals 4.6. Well, mu, I guess, okay, we're told that mu is equal to 15, I guess it's the same units. And then sigma is equal to 4.6. So the problem I had is that sigma, is that the, after getting 20, is that our estimate of the population mean? Or is that the sample mean? It says mean. You know what? I'm going to assume sigma is equal to sigma x. That means it's the standard deviation of the actual length. And this you may have to do from time to time. In real life, very often things are left a little bit vague, and you can't always go back to the people who asked you the question. And so you should get used to making assumptions. And if somebody says that's a bad assumption to make, I'll fine. But says that I didn't know any other way, and that's what I did. What's the expected number of defective parts produced above USL and below LSL? So expected number. Now expected number of parts produced when? Is this the expected? Is this the what expected number of defectives produced? Is that of the 20? So there's another question here. I'm going to assume, maybe what I should do is I should just have some assumptions, an assumptions box here. And I always, so one of the things that we can assume, there's a lasso effect. I can do this, and then believe it or not, I should be able to move that over there. Isn't that nice? Yes, thank you. Okay. Move that over there, and I also, well, I don't need to assume anymore, and I can again play this game, and it's there, okay, and that's one assumption. I'm going to assume that it's the expected defectives per day. So how many of the 120 are defective? That's what I assume. When it says produced, I produced 120 a day. So I want to know what percentage of those, or how many of those are defective. So I need to know what do I need to know? What's my next step? Anybody suggestion? No suggestions? Nobody's guiding me along? Okay, well in that case, I guess I better think of this. Well, I kind of like to think in terms of process capability, but let me write down something. Process capability gives me the percentage, the probability that X is between 22 and 10. Those are the good ones, okay? And so I guess the expected number of defectives will be 120, which is times 1 minus the process capability. Yeah? Anybody want to disagree? Agree. Okay. Yeah, that's right. You could attack this also. That's good. I think we're all on the same page. So here, I can do this, and this will be norm distribution 22, and then the mean is I given 15, and standard deviation is 4.6, and it'll be 1 at the end minus norm dist. What is it? 10? Yes, 10, and then ditto, ditto, ditto. Okay. So I go to Excel. Again, do I go to Excel, or you can go to Excel just as I can? And so here's something that I want to suggest, and it came up as a suggestion from discussing last Friday's session with Joanna. I think if you have computers with you, which you do, you have to, maybe you now want to go to Excel and do that, and then let me know what you got. Isn't 100 points per hour not? Oh, okay. Yes. I say per day. Yeah, I said per hour. Oh, expected number of defective parts produced. Well, I say in an hour. Expected number. Oh, yes. Thank you. I'm going to assume here per hour. Okay. Thank you for that. Back to you. Okay, 0.79. Thank you. So that's going to be 0.8. I'm going to call it 0.8. Okay, so that means that 100, so this is going to be 0.80 to 2 decimals, which means that the expected number of defectives is 120 times 0.2, which gives me 24. So of the 120 parts they produce every hour, about 20% of them are bad. Not good. Okay, so 100. So that's it. That's the answer, folks. We're done. Any issue? No. Pretty straightforward. Yep. But yet you had a lot of people wanted me to do this problem. So I guess you wanted to. Does the 20 come into play for this question? No. Well, okay. Let's look. Let me go back to this. If you were to assume, I'll tell you what happened. I initially assumed that it was sigma x bar, that it was the sample standard deviation, which is narrower than the population. So I multiplied by root 20, and I got a huge number of defectives. So I thought this can't be right. It must be that it was the population sigma x. And that's what I made the assumption on. So I first went the other way, got a ridiculous answer. Didn't think that whoever made up this question would want to see that the bulk of the pieces were faulty, and that's it. So it turns out that 20 plays no role in this. Can I use instead of, yeah, as long as you state the assumption. Just have a little assumption box and say, I'm assuming that the question wants to know what percentage of the 20 were defective. Okay, make that assumption and go with it. So I urge you to think of possible interpretations and then take the one that you think is reasonable, you want to go with, and that's it. You don't have to solve it for every possible. Okay, as long as you state it. If you don't state it, then the marker assumed one thing and you assumed something. That depends on the mood and the the clemency of the market. But if you state the assumption, then you bought yourself a little bit of an insurance policy. Unless your assumption is such that it would have taken a long time to. Well, I used the assumption that the beta formula was good for that case when you had to use the other control charts. By the way, I did post over the weekend. I hope you have it. I sent it out as announcement with an attachment that showed how to do that problem that I did on Friday, not just using the beta formula, but also the control charts in the from parts 3 and 4, I think it was. Okay. Any other question regarding this? We're okay? We're done. So next thing comes question 2. Sorry, question 1. Problem 1. Problem. So problem 1 is a bit of a theoretical thing. You have to prove that the ARL of 1 over alpha is that the ARL is in fact 1 over alpha. So this is to reinforce the notion that the run length is really a random variable and the ARL is just an average. So the way we would start is by saying, well, the ARL is the expected value of the run length. And let's call the run length, let's, instead of calling it that, let's back off a little bit. Let's just write it out for a moment. And let's say that let R equal run length. So it's a random variable. So the expected value will be, now the run length can take a value of 1, 2, 3, or 4. It can happen right away. So it's going to be, this is just taking expected value from basic principles. It's going to be that R is going to be either 1, 2, 3, 4, or to infinity. And the expected value will be the run length times the probability, I'll call it PDF, of R. What's the probability of it being R? So so let's then go to PDF of R and let's see what that is. It says use geometric, but I think we can argue our way to the geometric, because what we're going to say, it's a probability that now we're talking about an in-control process, that the false alarm on our sample. That means that the R sample is going to make us go out of bounds, and that could happen either the first time, the second time, the third time. Okay, let's think about that. If it happens the third time, or it happens on the Rth sample, it must mean that there was no alarm on the first R minus 1. So we would have, and the probability of an alarm is alpha, if you know from that little box, right? I'm not going to draw it again, but alpha is the probability that you have a false alarm, that the thing is out of bounds, but really the process is still in control. So it's 1 minus alpha to the R minus 1. So R minus 1, we're fine. And then you had a false alarm in that Rth one. Is that clear? Clear? Any questions? Nothing? Okay. So if we do that, we are not going to have that the ARL is that same summation, R equals 1 to infinity, and R, and we'll just change it around. Actually, you know what, let's move the alpha out here, because the alpha is a constant, and then 1 minus alpha R minus 1. There you go. So now, what do I do with this? Well, you know what, I'm going to take this guy here, and I'm going to call him a letter. I don't know what that is, but I'm gonna try to get some insight as to what that looks like. That's a sum. and I'm going to expand it. So when r is equal to 1, what does it look like? Well, 1 is equal to 1. Then 1 minus alpha to the 0, that's 1. So this is just going to be 1. And this is s. And when r is equal to 2, then it's going to be 2. And 1 times 1 minus alpha. And when it's 3, it's going to be 3. And then it's going to be 1 minus alpha squared. And then dot, 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 dot. It's just going to keep on going. Well, if you paid attention to proofs in high school, you would realize that you can multiply this s by 1 minus alpha, and then what are you going to have? You're going to have this 1 times 1 minus alpha. You can shift it over here. And this 2 times 1 minus alpha is going to become 2 times 1 minus alpha squared. Are you with me? And so on and so forth. And then if you take the difference, you're going to have s minus 1 plus alpha. This is going to be alpha s. You with me still? And this is going to be interesting. This is going to be 1 plus 2 times minus 1 times is going to be just 1 times 1 minus alpha. And 3 times minus 2 times is going to be 1 times. This is 1 minus alpha squared. And so on and so forth. Well, if you remember, you can, a over 1 minus r is the infinite geometric series, a over 1 minus r, how you calculate these. I still get money, $42 a month from my having been on staff for a few years at the University of Manitoba, because they converted my pension into an annuity. And there's enough there to pay, there was enough there to pay me out $42 a month for forever and ever. Okay, anyway. What is this? So A is 1. 1 minus r is 1 minus 1 minus alpha, that's alpha. So what we have from here is that s is equal to 1 over alpha, long way. 1 over alpha squared. You got that? Well, if we do that, then we go back up here, and this is alpha times 1 over alpha squared, and we get 1 over alpha, and that's it. Ta-da! So we've done it. I know what you're going to ask. You're going to ask something like, do we have to be able to do this? And yes, there's nothing earth-shattering here. Could we do this? Could we do it the same way as beta, that since r follows the geometric? Yeah, you could. You could also be asked to prove 1 over 1 minus alpha. 1 over 1 minus beta. How do you know that in fact, we could have asked the same question. Instead of asking you, prove that ARL is equal to 1 over alpha for in-control process, hint, we could have asked, prove that ARL is 1 over 1 minus beta for an out-of-control process. And you could do exactly the same. You would prove it exactly the same as you just did. I don't know if that was your question, Brenda. Can I show it again? All right. Let me go where I was. Okay. So the first thing is the ARL. You have to know that it's the average, and the average and expected are interchangeable terms. So it's the expected value, and the expected value is the product of how much, in other words, if I take the expected value of a die, okay, of one die, well, each one has an equal chance of getting 1 or 2 or 3 or 4 or 5 or 6. So I just add up those numbers, 6 plus 5 plus 4 plus 3 plus 2 plus 1, and divide it by 6. And that's my expected value, because each one has an equal chance of getting that value. Take 2 die, it's a bit dicier, sorry the pun, because 2 6s, there's only 1 out of 36 ways of getting 2 6s. And there's only 1 out of 36 ways of getting a 2, a 1 and a 1. But a 7, you can get a 1 and a 6, a 6 and a 1, a 3 and a 4, a 2 and a 5. So there's many ways. So the different. So if you want to know what the expected roll of a die is on the long run, you can calculate it by multiplying the probability times the number on the die. And so what we're doing here is using the same concept. We are multiplying what the run length could be, the random variable, times the probability. I just called it PDF because that's what I always use, but I could have put down probability. I wrote down here. PDF of R is the probability of a false alarm on the rth sample, right? And that's the expected run length. These are all the, R is all the possible values. I know that I'm pointing with my pen, but you can't see that. So I don't know if, I just want to find out if there's a pointer here. If I don't know. Okay, you see the screen here. I am. No, don't want to draw anything. Anyway, so let's go. I'm at the front. I'm at the top row now, and I finished explaining that the ARL is the expected run length, and we make up a letter. Let R be the run length. And so this second row is like getting the average roll of a die. It's taking every possible value of the run length times its probability. Now the only difference here is that that value, instead of taking 1 out of 12, it can be a 1, a 2, or 3, or 12, or 13, or 14. This can be any number up to infinity. So the sequence is going to go up to infinity. And now I need to know, so I'm done there. Now I go down here and I say, okay, what's the probability of having a PDF of R? It's the probability of getting a false alarm on the rth sample. That is by definition. And then I think about it and I say, okay, if I do that, I get, if the rth is a false alarm, that means that R minus 1 were not false alarms. So it's 1 minus alpha to the R minus 1. And I now have a false alarm on the rth sample. So that's that. And that's a geometric distribution. But I didn't use the hint. I just argued my logical way through this. But if you wanted to, okay. So now we get to the next line. We continue. Now we substitute this expression here into the ARL that we wrote down earlier. I moved the alpha up front because it really doesn't depend on R, so it's a constant. I moved it up front. Now I have this complicated expression, and I don't know what to do with it. So, like in any of these quantitative worlds, if you don't know what something is, give it a. Once you give it a name, things start to roll. So I'll call it S. So all right. So now I call it S, and I say, okay, what is S? Well, let me get to understand what that expression says. And that expression says that S is equal to 1 the first time. The second term is 0. The second time is R will be 2, and this will be 1 minus alpha. The third time will be 3, 1 minus alpha squared, and so on and so forth. Okay, I get the meaning of this. Now I say, hold on a second. I know this from high school kind of tricks. I have to find an expression for S. Sometimes when you multiply by what's multiplying it, you get somewhere. So this may have been experience on my part. Hopefully it's experience in your part too. And you can multiply both sides by 1 minus alpha. So when you multiply the left side by 1 minus alpha, you get that. When you multiply the right side by 1 minus alpha, the 1 becomes this guy here. The 2 becomes this guy here, right? You get the idea. And then once I have that, I can subtract both the left side and the right side. On the left side, I get 1 minus 1 plus alpha times S. And on the right side, I get something really nice. I get a plain old geometric series whose formula I know from high school, A over 1 minus R. I can also derive this, by the way, but that's another story. And so A is the first term, 1 minus R is 1 minus 1 minus alpha, which is again alpha. And so S equal to, by moving this alpha down to the other side, I get that. So now I know what S is. Once I know what S is, I substitute it back in my ARL equation, and voila. Could you show, okay, can I show it again? Yes, I just did, Glenn. Could you show for out of control beta, just the initial, it's exactly the same. If you do it for the beta, you're gonna get, it's gonna be the same here, it's gonna be the same there, it's gonna be, instead of this, it'll be a true alarm on the arts sample, okay? So this one will be a true alarm. If it's out of control, instead of false, it will be true. And this one will be beta to the R minus 1. Think about that a moment. What will it be? So I have a true alarm on the R sample. That means that I didn't have an alarm. What is the, I need to draw that little box, you know, the box that has, it's not big enough. The box is alpha, 1 minus alpha. It's beta, and 1 minus beta. So we're talking about the type 2 error. We're talking about it. This is being out of bounds, but really the thing is still out of control. This is in bounds. This is in control, and this is out of control. This is control, and this is bounds. And so for the in control, I had so many 1 minus alphas, and then I finally had an alpha. For the out of control, I'll have so many betas, and then I'll have 1 minus beta. Okay. So now, so this turns out to be beta to the R minus 1, and then 1 minus beta. Yes? And then you do the same thing. You replace that in there. You call that S. That's the initial setup. I hope I've done the initial setup anyway. Could you show part of control beta just the initial setup? Q. I did that. In the video today, it just concluded ARL 1 over 1 minus beta since beta falls to geometric distribution didn't go through and as detailed the proof. Yeah. And in fact, I appeal to your intuition. Okay, remember I said if the probability is 1 minus beta, and I want to express the 1 minus beta as the number of events, then I just, you know, if something has a 50% chance, then one out of every 2 times. Okay, this is, you know, somebody might say, well, isn't that a proof? Not in the same way. So I didn't go in a detailed proof. I just appealed to your intuition. I must tell you something, anecdotally. I teach a course, and for years I had to, there's some conditions called current KKT conditions in operations research. And for years I taught this as an undergraduate course, and I thought I had it proved. I drew a little diagram. I showed how obvious it was, and I thought I had proved it. And then I taught a graduate course in it, and it took me about 4 or 5 weeks to prove the result, and had to use umpteen theorems and sort of who knows what. So the standards for mathematician proofs are a little bit higher than your regular intuitive kind of argument. That's it. Yes. So we're all right. So now I am at 25 to 5, and I'm at exercise. So we did problem 2, problem 1, and now we're into, well, what was there about the exercises? Let me just see exercise 2. I only have the question here. I don't have the solution here. I have my solution, but Yeah, which control chart is suitable? Is control chart for attributes, since it's discrete. Which particular control chart is he using? Well, we have two control charts for those. We have the P, which gives you the proportion, and we have the NP, which gives you the number. And since he's interested in the number, then the NP chart would be the one. And then you have the data for exercise 1, problem 3. And you have sample means and ranges. And you can find the percentage of non-conforming products. Pretty similar to the kind of logic that was here. Not that much different. That means what's the probability? It's 1 minus the probability that you will be within the bounds. And you can get the mean and the standard deviation based on the data that is provided. Now, since the data is provided in terms of range, you have to use one of those D2 for, I think it was a sample of 5, right? Was a sample of 5, and that we are okay. Yes. So I think we're okay. Let me, if you have specific questions, please shoot them this way. Okay, just as a I think by now the solution should have been posted of assignment 4, I hope. And also, there's going to be 2 problems in tonight's assignment. So we'll distribute the email soon. And any other questions? Well, if there are no further questions, then we'll quit a little bit early today. Let me, where's the assignment post? It should be there. It will not, yeah, it's time to appear at 5 o'clock. I might go in there and attach it to the email. That's what I'll do. I'll attach the question to the email that you sent out if I get there before. Can NPL greater than 3 sigma? The natural, no. Can the NPL. The NPL is the natural limits. That means the actual variability of the individual units, not of the mean, but not of the sample mean, but of the individual units. And the Shewhart, okay, maybe this is something that a lot of people have problems with. What the heck is a Shewhart chart? So Shewhart chart is all these charts where you use as a rule plus or minus 3 standard deviations. Now you might say this number plus or minus 3 standard deviation is kind of arbitrary, which it is. But that's now people have gone to 6 sigma and have tried to tighten things up. But still the plus or minus 3 sigma is still in wide use. That same 3 sigma that is being sort of cast in stone for the sample mean has been cast in stone for the natural tolerance limits, which is the actual variability of the individual unit, not of the sample mean. So it cannot be greater, well, it can be if you change that 3. You can set that to any number you like, but the custom and the tradition is to use, if you follow the Shewhart chart, then it will have plus or minus 3 sigma. Assignment solution will be posted. When to choose NP chart, when to choose P chart. Okay, that was the purpose of that exercise, which said the engineer stops the process if at least 5 shafts do not pass the gauge. Which particular control chart is he using? So since he's talking in terms of the shafts, 5 shafts, he's not talking about the percentage. In fact, I don't even know how big a sample is, so I don't know what percentage of defectives there are. So since he's dealing with units, then the NP, it gives you the number of units. So that's, when you want units, you use NP. When you want proportion, you use the P chart. Winking, is that okay? Where's the assignment solution post? Okay, well, I met Abu down the road, and he said that he had posted it. Maybe he's still in the process. It's coming soon. Before the end of the day. It is posted, Justin. Thank you so much. So, anything else? Tomorrow, okay, yeah, I was going to say something about the days. So, my own personal take on this material is that the basics are pretty straightforward and a bit dry. When we start worrying about detecting small shifts or detecting rare events, like your quality is so high that you keep on taking samples after samples after samples, and there is no defects, right? And you just can't collect you just can't collect enough samples to generate to get a defect. Then things become interesting all of a sudden, because you have to think a bit out of the box, and you start monitoring the time between defects. That's interesting. And also, when you have to detect small shifts in the mean, then you have to think of novel approaches. And QSUM and UMA are novel approaches, not widely used yet, but they really do catch the defect. I've used a simulation model to test, like, could I catch the defect? Does an alarm go off with the Shuhart charts? No. Does an alarm go off with these new charts? Yes, they do. They actually work better. And deriving them is a bit more interesting. So I sort of wake up myself to this material as we progress in this week. So I want to sort of share that enthusiasm, at least with you, that some of the stuff that we're going to be talking about is interesting and a bit more enjoyable. So that's it, folks. See you tomorrow, bright and early. Take care. Good night.